Hi guys, welcome to my channel. In this video, I'm going to explain you about the uninformed search algorithms, which are depth first search and breadth first search. And I'm making this video to students to help students who are preparing for GATE, end semester exams, interviews, and other competitive exams. And I'll explain in the most basic manner, so such that anybody can understand both breadth first search and depth first search algorithms. Uh, you don't need any prerequisites, guys. I'm explaining in a very basic manner. So just be with me, guys. At the end of the video, you will be expert in both depth first search and breadth first search algorithms. Okay, now let us start with depth first search. Depth first search is one of the uninformed searching algorithm. Hmm. What is uninformed search algorithm? Like we don't have any prior knowledge about the goal node. Let us see, like here it is the initial node, which is A. From starting from A, we don't have any parameter, which will say C is better choice compared to D. So we need to explore all possible nodes till we reach the goal state. So we don't have any prior knowledge about the goal node. We have to explore all possible vertices, one, two, three, all possible vertices until we reach the goal vertex. So now, how? Let us see how depth first search algorithm works. So, okay, guys, let us see by this example. Now, here A is initial state. We consider A as initial state. And depth first search algorithm uses stack data structure. Now, first we will insert A into the stack and we will check whether A is the goal state or not. So, simply A is not the goal state. So, the algorithm will pops out A and pushes its children like B and C into the stack. We can put in any order, like we can push first B, C, or C and B. So order don't matter, guys. I'm just considering in this way. So let us push B and C into the stack. Now B is in the top of the stack, so the algorithm will explore B. Now it will check whether B is the goal node or not. So simply B is not the goal node, then it will pop out B and pushes its children into the stack, which are D and E. So again, the algorithm checks whether D is the goal node or not. Simply D is not the goal node and it don't have any children. So it will pop out D. And again it will check whether E is the goal node or not. E is also the goal node. So it will pop out E and it also don't have any children. Now the only element left in the stack is C. So it will explore C. Now it will check whether C is the goal node or not. No, C is not the goal node. Now it will pops out C and pushes F and G into the stack. So now F is on the top of the stack. So now it will check whether F is the goal node or not. So simply F is not the goal node. Now it will pop out F. And the only element left in the stack is G, which is nothing but the goal node, and the algorithm will get terminated. One thing can you observe, like first it explored A, then it explored B, then it explored D. So it is going into the depth of the tree, like it will go deep into the depth of the tree and then it will come back. That's why this is called as the depth first search algorithm, and this is one of the drawback in the depth first search algorithm, which I will discuss later. So this is basically the working of depth first search algorithm. Okay, guys, now let us see what are the drawbacks of the depth first search algorithm. I'll consider the previous example only, but with a small modification. So here you can see there are infinite number of nodes connected to the node E. So after reaching the node E, we are having infinite number of nodes connected to E. Let us assume like these are infinite number of nodes. But the goal node exists after C, like in this particular path. So initially, what I said is depth first search algorithm is uninformed search algorithm. So we don't have any prior knowledge regarding the goal node. So after exploring the node A, we have two possible choices. We can either go to B or to C. So both have equal priority. So the algorithm may choose either B or C. Anything could be explored. Now let us assume the algorithm had chosen B as the next node after exploring A. So initially A is pushed into the stack, then it will be popped out as it is not the goal node, and both B and C are pushed into the stack as both the children of A. So now algorithm had chosen B to explore after A. So as B is not the goal node, it will push both D and E into the stack. It pops out D, and it explores E, and it pops out E as it is not the goal node, and pushes I and J into the stack. Now it pops out I and explores J, and pops out J and pushes X, and again pushes the children of X and explores whether they are goal or not. And this loop continues and will never gets terminated. And the algorithm is stuck in an infinite loop, which would never lead us to the goal node. This is the drawback of the depth first search algorithm. Even though we can reach the goal node, but the algorithm just is stuck in the infinity loop because of this infinity number of nodes. So whenever there is an infinity loop or infinite number of nodes, present in the tree, then the algorithm may there may be a chance that the algorithm may stuck in this infinity loop. So that is the drawback of the depth first search algorithm. So now let us see what are the time and space complexities of the depth first search algorithm. Okay guys, now let us see what are the time and space complexity of the depth first search algorithm. So time complexity. So depth first search algorithm in case of a graph. So guys, let us assume a simple 4 vertex complete graph. So there are 4 vertices A, B, C, D. Let's assume. So this is a complete graph, and A is initial node, B is goal node. In case of a complete graph, after choosing the initial node, from starting from the initial node, we have three possible choices: B, C, and D. We can choose either B or C or D. So, in worst case, like if we choose B first, then C, and then D, we have explored all the possible nodes which are present in the graph. That's why the time complexity for the depth first search algorithm in case of a graph is order of vertices plus edges, because in worst case we have to explore all possible nodes till we reach the goal node. Similar to that, in case of a tree also we have to explore all the possible nodes. Simply like there is a small tree. Mm. So then this is a small tree. So in this case, this is goal and this is initial node. So in worst case, if we come from this order, then we will go here, here, here. So in this way, we have to explore all possible vertices that are present in the tree until we reach the goal node. So that's why in case of tree also, the time complexity is order of vertices plus edges. Order of vertices plus edges. So space complexity. So again, let us assume a small complete graph with 4 vertices. So A, B, C, D. G is goal state, B, C. So space complexity in case of a graph. So for a depth first search algorithm, if A is initial state and G is goal state, after initial state we need to explore all its adjacent states as it is not the goal state, which are B, C, G. So we need to put all the adjacent or all the vertices of the graph into the stack B, C, G. So we need n total number of vertices minus 1, total number of vertices minus 1 space in case of a complete graph for a depth first search algorithm. So this much space is needed for a stack. That's why the time complexity will be, as 1 is constant, we will only put it as order of vertices plus edges. Order of vertices, not edges, or order of vertices. Similarly, in case of a tree, let us assume a small tree. As we remember, the depth first search algorithm searches into the depth of the tree Let us assume the goal state is